So if it's about zeros and multiplicity, but we have a really important add-on that I have to teach you. It's called limits. This has a couple zeros. How many does it have? 3 of them. What's it doing at that one? Bouncing. What's it doing at that one? Cutting through. What about that one? Cutting through. Now, sometimes we make the distinction that this special kind of cutting through is an x to the 3rd power, but don't stress about that. As long as you just call it a cut through, that's fine. Okay, but I can tell by looking at that that's an x to the 3rd power versus an x to the 1 power because of the fact that it's an inflection point. Do you get that if you read from left to right, this thing was increasing, but it changes the way it's increasing at that exact moment? It goes from increasing slower and slower to increasing exponentially. Do you get the difference? It's like it's increasing the whole time, but it changes, and that's called an inflection point. That is something that they say happens when you're like in an S adoption curve for something, for example. When all of a sudden something takes off, it's like, ooh, we're at an inflection point. And a lot of people would say that we're in that neighborhood now for electric cars. They're getting faster and faster adoption. Granted, it's still 96% gas, but all of a sudden it's going to be like inflection point. Whoa, everybody's talking about electric cars, and it's going to go the other way. Okay, so that's an inflection point. That's an x to the 3rd. You see it in this graph. If I graphed you x to the 3rd, do you see how that's supposed to be an inflection point right there? I didn't make it perfect, but that's a special kind of cut through. That's all I'm saying. All right. If I gave you a list now of the zeros and asked you what was happening, I think you could all say cut through or bounce. That's easy. It's going up on the right. There's a fancy way to say that that's really important, and it's called a limit. I need to teach you that. I'm going to write you your first limit that you've ever, you might have seen one on the sidewalk. It's a pretty classic thing to tag a building with, is a limit, of course. The limit of the function... That was a joke, by the way. I'm aware that nobody tags buildings with limits. Of course, nobody's a big word. The limit as x approaches infinity is infinity. Now, these 2 spots right here are where you put your x and your y values. But I'll just break out the other part and put it in blue. In every single limit statement you ever write, you'll write this: the limit of the function as x approaches something is something. And I'm going to put question marks there. It's pretty obvious which of those 2 is the x value. You're describing that down with the x. And the x goes to the arrow. That's pronounced approaches. Okay, so if I said that this was the right limit statement for this graph because it's going up, why can't you just say it's going up? Well, because there's different parts of the graph, and I want to say it's going up on the right end, but it's also going up on the left end. So how could I write that in a limit statement? And why can't I just say it's going up? Well, because sometimes it goes to an exact number. In other words, like, for example, would you agree that the population of deer won't just do that forever? In the limit, we would all be walking around, like knee-deep in deer. They'd be everywhere. You couldn't even get to your car until you, climbed over 17 deer. Why doesn't that happen? Well, because it levels off. There's an inflection point at some point, and it levels off. If there were only 2 deer and there was no predators and they weren't allowed to be hunted or anything, yeah, it'd grow pretty fast. There'd be a lot of deer all of a sudden, but then it would level off. Why? Unchecked without any predators, what would happen is your deer population would spike and then it would crash. How would it crash? Because they run out of food in the winter specifically. In the summer, there's plenty of food for them all over the place. But in the winter, up here in this area, that's what the deer population would do. In a place like, like Tennessee, there could be lots of deer. And they're going to be just mostly limited by the predators to the deer. Otherwise, there would be deer everywhere. And it's only because things eat deer that keeps them from being like everywhere. Because eventually, I mean, there's lots of grass and there's lots of trees that they can nibble the bottom branches from. But this is what would happen in Minnesota: is the deer population would plummet like this if there weren't any predators or hunting at all of the deer. Okay, so back to a population that looks like kind of stable goes like this, and it levels off. Because there is some logical limit to how many deer there would be based on how much habitat there is and how many predators there are. And they're trying to just kind of keep it level-ish. I know in the real world there's going to be still some dips and valleys, but this graph doesn't have a limit of infinity, does it? Let's say it's per square mile to keep it simpler, because otherwise, like, what are we talking about? Let's say it's how many deer per square mile there are, and let's say 100 is the natural, kind of normal, stable limit. Well, then I'd say that the limit, in fact, I want you to write the limit statement for deer. Liam. See if you can finish it. So, while you're working on that limit statement, I'll give you an example of somebody talking about in the limit, because they say this in like regular conversations. If you're kind of an engineering, sciencey, mathy sort of person, and they're talking about things, they'll be like, well, in the limit, that would mean that, basically it means if we keep extending this forever, that would mean that. And so, for instance, there's so many different topics. I'm just going to try to think of one that's not controversial. Okay, would you agree that Facebook is not going to have 8 billion people on Facebook? That would be every person in the world. That's not likely. But they've already got, I think it's over 1 billion people on Facebook. Probably Googleable, like they have maybe 2 million or 2 billion people. I don't know what it is. Maybe it's 1 billion, maybe it's less than 1 billion. But there's some natural number that in the limit will be how many people that it will tend to be. Because not everybody's going to want to be on Facebook. You guys aren't even on Facebook.
2.7 billion.
2.7 billion. Holy crap. Now, you might be like, that's half the world. That's impossible. And it's also possible that some people have 2 accounts. That happens a fair amount. How many of you guys are on a social media site and you have 2 accounts on that site? Yeah, there's a lot of you. Probably heard of the Finsta. All right, anyway. So, and maybe it's the account that you're on with where grandma's on the same account as you, and you don't really want grandma watching all of the things you do, so you got 2 accounts. Okay, so anyway. So, in the limit, the deer population as x, which is like time, approaches infinity, the limit of our function for the deer population is the height of it would be 100. Does that mean it'll hit exactly 100? No, it'll approach 100. It'll get infinitely close to that. So, how about this graph? You remember this graph? Y equals 1 over x. You have that one in your memory banks? What's the limit of it? And there's a left-hand limit and a right-hand limit. I want you to sketch this one, and then I want you to write lim for the right side over there, and lim for the left side of the graph over here. It's called the left-end limit and the right-end limit. And hint, there are infinities involved, but there's also other numbers. So this isn't just all about infinities. Sometimes it's other numbers. I'll pause for a second while you write that limit statement. So as x approaches what? So say it to me. The limit as, no wait, I actually said it wrong. The limit of the function as x, keep going, Solani. So if I go way, way, way to the right, then what's the y value? 0. What wouldn't be what?
Why wouldn't there be 4 limits for each?
Oh, there is more than one limit, but I said the right end limit. That's
What,
the right
are there
end.
2?
Are there other limits? Yes, just wait. You asked, are there 4 different limits? Yes, there are, but right now I just asked for the right end limit. Now let's do the left end limit. The left end limit.
Ooh, I got this one, I think.
Fire when ready, Pats. Limit of the function.
The limit of the function as x approaches negative infinity is 0.
Negative infinity is 0. You got it. You caught on. Now, this middle two limits, that is not something we even test on in this unit. But I know some of you are going to be curious about how you could talk about this area
This one.
right here and how, you know, it's going up there. And like, how do I even talk about that? It's in the middle. Well, you can start with this. I said every limit you ever write will say lim of the function as x approaches something will equal something. And wait, we said 0, and that's not what I meant to put. So wait, I just want to say that's the starting point. And all we have to do is figure out what goes here and what goes here. So for that blue area there, would you agree that Nick was right that x approaches 0? I know it's hard to say that Nick is right. I mean, that's difficult for most of you to say, but
That was
I
me.
said yes.
all right. So
That was you.
x approaches 0. If x approaches 0, but wait. If I was in this area here, x would also be approaching 0. So we have to say from which side it's approaching. Is it approaching from over here and heading this way? Because that's one kind of limit. And then there's another one where you're heading this way. You were coming from the left. I wish it was as simple as left or right, but it isn't. It's x approaches 0 from the positives. Wait, I got to put right here, I got to put a little plus. X approaches 0 from the positives. The other part is easy. What will y approach? If we're in the blue zone here, it'll be infinity. You're correct. Okay. I can tell that Mr. Busselberg really wants to do one. So you do the green zone, Mr. Busselberg.
good.
Prove you got this. Come on, you got this.
Okay, since you're so confident.
Lim of f of x
Yes.
is equal to negative.
Wait. We got to say the x approaches first.
Oh, sorry, x approaches 0.
From the
Negative.
boom.
And then it's equals negative infinity.
You got it. And just so you know, that is harder than anything that we would do. But we would do a lot of things like this. Here's a strange graph that goes up and stops right here on this end.
Very straight right there.
And it goes down and it goes to negative 20 down there. Maybe this is the operating limits of submarine / plane. Is there anything that can start underwater and then go up into the air? There is. There are things, not just James Bond cars. There's actually things that can do this in the real world. So,
Are you saying that James
would you
Bond
tell
cars
me what the right end limit of this thing is? The right end limit.
Limit of the function.
Mariam, you got this? Limit of the function. You're going way to the right. X approaches infinity. Equals 100. Very good. Left end limit. Let's go with Nathan.
Wow.
Limit of the function. Can you finish it from there? Mr. R, you got this? Limit of the function as x. Give it a shot. If we're going way this way, what is x approaching? If we're going to the left end, what's x approaching? I can't draw any further help. Negative infinity equals negative 20. Perfect. There is your left end limit. We're not going to do inside limits in this chapter, so I'm going to stop talking about approaching from the left or approaching from the right, but I just threw that in there for the extra smart kids. You decide if that's you. All right. So now I actually need to get to the rest of the slides in here, but I needed to teach you that. It was a super critical thing. It's called limits. You're going to be learning them this year and then using them a ton. Next year, you'll have like a whole month of limits where you get more and more complicated things with limits, but that's really important to me to set a good foundation for you knowing limits in calculus, in Calc 2, etc. Yes?
In those lower problems, does having an arrow on the end of the graph make a difference?
Yes, it does. So in most cases, if I just draw this, it just means I forgot to put an arrow on it. But if there's a stop point right there, if it's got a dot, then we're specifically saying it doesn't continue.
So if there's a dot, we treat it like it stops. If there's nothing there, we treat it like an arrow.
But you should really ask. Just go ahead and ask. It's okay to say, is there an arrow on that or not? Because it matters. All right, back to this. Would everybody get to this warm-up page and tell me, you should know what the leading term, the degree, the leading coefficient, and the constant are. If you don't know any of those, it's okay, but I need to correct that because that's a weakness that would come out and bite you at a critical moment on the test. Pausing for a second. All right, I had kids just make a quick sketch of this, and the reason that it bounced right here was because at this root, which would be a half, because that's the thing that makes it 0, and zeros and roots are the same thing. At that spot, there's a bounce. That's why I made it bounce there. And then why is it going up? Because there's no negative on the lead term. And then why is it going down on the left? Because these are going opposite ways, because that's odd. Does that all make sense to you guys? All right. That's a lot, I know, but we need to move on. All right. This is just about sketching. We already did just do that one. Would you please sketch this one? I totally get you won't know the x-intercepts because it's not factored. If you can factor it, you should, but we can't factor this one, so don't. I don't need you to write the limits for it either. All I care about is the graph right now. I understand you have to go. I'll take that back. You know, I know you've been absent some. I don't know if you caught this stuff lately, but can you do this? Left end, right end, y-intercept, any of those?
I know some of the rules, but I don't know like where I would start.
Okay,
Like, if
here's
had
where I
starting
would start.
position,
What do you think that is?
That's the y-intercept.
Start there. Go ahead, put a dot there. Then you'd think, well, I don't know where the x-intercepts are because I can't factor it. Then you should just be thinking, what should it be on the right side? Should it be up or down? Heading upwards or heading downwards on the right end? And this tells you. Nick explained that to him because you were here.
No, it wasn't.
Boo. You watched the video though, I'm sure. Oh, maybe not. Okay. Jada, you were here. That negative in front. What does that tell us about the right end?
It tells us that the right end is going downward.
Good. It's heading downward on the right. Okay. Carter, can you tell me about the left end? Hint, it's either the same or it's different than the right end. It's the same because why?
That was such a good tip.
That 6 is either going to be even and then it'll be the same, or it's odd and then it'll be different. Nick, I know what you're saying, but it is a good hint, and what you just don't understand why because you didn't watch the video. That is that even or odd number there, that degree. If it's even, they're the same. Is it even? Yes. So they're the same. Okay, so it's going down on both ends. All right. Now, if you're lazy Larry, and I don't blame you for being lazy Larry, that's all you'd have to do to get credit. You're done. Now, if you wanted to be more meticulous, you might be able to be like Super Silva and try to go a little extra. And maybe say, oh, I know that it's got 5 turns in it. So you can do like do. You're right, maximum of 5 turns. 1, 2, 3, 4, 5 turns. Yay. So there. But wait, just wait. The reason it can have 5 turns is because of this number. If that number is a 6, you can have always 1 less than that number of turns. I'll prove it to you quick side for those that didn't watch the video. This is y equals x squared, which has a 2 in it. And how many turns does it have? Only 1. It went from heading south to heading north there. And that's 1 turn for x squared. See how that works? Okay, so if it was x to the 12th, there could be up to 11 turns in it. So now Super Silva was so obsessed with getting the perfect number of turns that, not that you would have done this, but it's got the wrong y-intercept. So I better maybe just take out, and there's nothing wrong with this. You can just take out some of the turns because it just has to have 5 turns or less. So then I can just go through there and it wouldn't matter. The other turns are representing imaginary things which you can't see anyways. So this would also get credit because all that really gets graded on this kind is the y-intercept and whether it's up or down on the left and right.
Could you have also done the one with 5 turns, but just shifted it over so that it went through
Yup,
-3?
yup. You could have still stuck with 5 turns and had it go through -3. I agree. Okay, but I'm just trying to show you don't even have to have exactly 5 turns. You just have to have less than, well, you can't for sure have 6, but you have to have 5 turns or less than 5 turns. All right. Now I got to get to the most important problem that we didn't do yesterday. That would have made it even more ludicrous. It was already hard to do, especially on a math day that was shortened. But this problem is critical. You need to understand this. I can't believe I haven't by now got a piece of cardboard and made this so you could hold it in your hands, because this is really, really important to understand. Not just because we're going to obviously be tested on something like this, but because it's a really good example of a polynomial in real life. Okay, so I think you can visualize what a piece of cardboard like this would look like, where you could cut out a corner and each corner, and can you imagine folding on the dotted lines and it would turn into a box? Can you picture that? Okay. Would you agree that x implies a varying amount? I could cut out a little tiny corner or I could cut out a really big corner. But do you get, if I want to be ludicrous, since it's a 10-inch long side there, I can't cut out 7-inch corners from each side, can I?
You can try.
No, you couldn't. It just wouldn't work. Okay. Well, you could try, but you would fail. Okay, that's true. All right, so I want to know what's the domain of x. X has to be between what and what. Don't say it out loud, please, because I get it. Once you hear the answer, you're going to be like, well, yeah, it's obviously that. What's the domain of x? X is how much we're going to cut out for the corner, and it can't be smaller than this. It has to be at least this, and it can't be any bigger than that. Everybody think it through. I'm going to pause for a second while you think through. What sizes could you even cut? Talk to the person next to you. Oh, you can't have 0, and you can't have what? I heard 5. Why? Well, because if you go over 5 inches here, and then you go over 5 inches there, you just won't have a box anymore. It'll just be gone. It'll be like a big flat thing. Okay,
I still think I can hit 7.
so that's the domain. Notice, a lot of kids are going to say 6. And I get it. Do you know why a kid would say 6? And it's wrong, but do you know why a kid would say 6?
5 plus 5 is 10.
It's not about 5 plus 5 is 10.
The 6 is 1.5.
I do not get it then. Oh, because 12.
Because of the 12. They're going to look at that and go, well, see, you can cut a bigger side over there, and so I'm going to say x can be up to 6, because look, on that side it could be. But then if you go 6 in this direction and 6 in that direction, it is not going to work, right? So you got to take the smaller side, so you couldn't say 6. All right, next, would you agree that a box is essentially length times width times height?
Essentially, yes.
That's the volume of a box, right? But we know more about it than just L. Always pick the longer side, which between 10 and 12, I'll help you out, Nick, it's the 12.
Oh.
Okay?
Thank you, Mr. Sherman.
You betcha. So we're going to say the length is 12, but it's not just 12, because we're going to cut out some sides. Okay, so it's not just going to be 12 times 10 times x. A lot of people, that don't understand this would say that, but that's wrong. Would you please change this to be right? You need to adjust it a little more to have this be length, this be width, and that be the height of the box. And write me a correct formula for this box. I'll pause for a second while you give that a shot. It's kind of like this, but it's definitely got to be more complicated than this. Okay, so I hope you were able to comprehend that this 12 had to be not 12, it had to be less than 12 because we're cutting part of it off. And I get 12 minus x would be a feeble attempt, but what would the actual right thing be?
Not my feeble attempt, apparently.
12 minus, well, wouldn't you be subtracting x from both sides? Did anybody come up with 12 minus 2x?
That's what I had.
A few of you would have got it the first time. Hopefully many of you will get it the second time. The other side isn't 10. Talk to your partner about what it must be.
10 minus
10 minus
I got it.
2x.
See, 10 minus 2x, because you're subtracting it from both sides. And then the height is still x. For some people, a little settled would be appreciated. That x is the height, and why? Because when you fold the box up, it's the third dimension. The box was kind of two-dimensional, and then you build up the sides, and you got a height of x. So there is an equation. Now, if you were to graph it, would you agree it would have roots? Could you make this part equal 0? Could you make that part equal 0? Could you make this part equal 0? Yes, so there's 3 roots. Watch, one of them's here. One of them's, what would make that 0 if x was what? 6. What would make this 0 if x was what? So then, there's the zeros, and then what's it going to do? I would propose that it's probably going to do something like this. Is there any squares involved? So then it's going to do some weird thing like that. Well, wait, that can't be right. I know it can't be right. You know why? Because I've included something that's impossible. Could you possibly have an x that was less than 0? No.
'Cause you
Okay.
can't have negative box. Like,
And now, what was our x constraints? X could only be between what and what?
0 and 5.
0 and 5. Now, I want you to think about this. If this is how long your x is, do you get that the super tiny height of a box, do you get it wouldn't hold very much? So this is volume. And the volume wouldn't be very much if you had a teeny tiny x. At some magical amount, you'd get the biggest volume box. As you slowly increase x, the volume will get bigger and bigger and bigger until you've increased the x too much, and now your box is getting skinnier and skinnier. And then all of a sudden, if you have an extremely high box height, it's incredibly skinny and like it'll hold a pencil or something at the end because it's so tiny and narrow. So do you get how the volume will go from really small to really big and then back to really small again if you keep on increasing that x? Do you see how that polynomial makes some sense? The volume will have this maximum right here where x is some magical number. Is it exactly between 0 and 5? I don't know. I'd need a calculator, and that's what it says you should do. I don't need you to do that right now. But if you did, you could put this in your calculator, and you'd be able to figure out where it was at its peak. And you'd be able to go, that's my spot. That's the spot that maximizes the volume.
Numbers are crazy.
All right. You're going to have a problem like that on your homework for tonight. Yes?
wait, so after the 6 or after the 5, nothing that doesn't exist?
Well, because, think about it.
Well,
It doesn't
okay, but-
exist.
Yeah, I understand.
Right.
Like, why,
So we can just erase all of this
Okay.
because we said that we knew from looking at the problem there was no way for the graph to go any bigger than 5.
all right, and then you would draw.
And in
an
fact,
open
it
circle?
can't even be 5.
Yeah, you draw an open circle.
Yep.
Okay, I was just confused. 'Cause
Very good.
We were supposed to draw that.
You're just freaking me out because you're thinking deeply like this. I'm like wondering
Yes, I'm
what's
thinking
going on.
You're right, my bad, guys. I'm just
Okay.
trying to.
So you're right. It can't be 0 and it can't be 5. It's got to be somewhere in there. And as x goes up, at first the volume will go up. And then do you get how at some point the volume starts going down because your height has gotten so high that your box is getting smaller again? If you can't visualize that, I do understand. But if you take this box, do you think they set up Kleenex to have the ultimate volume? Well, it depends. Which is better if use of the space? Is it more like the cube or is it more like the rectangle? Well, they might actually just be going for an aesthetic. Maybe people, they poll people and they see how many people like the more rectangular looking box of Kleenex and who out there likes the cube. The ultimate thing would be a sphere.
I don't see how that would be practical.
A ball of Kleenex wouldn't be terribly practical, but it would maximize how much volume you get for how much surface area you have.
It definitely wouldn't maximize
All right.
manufacturing.
You're right, and storage, and there's all kinds of things. So do you get how it isn't just about the biggest volume you can get? It's going to be about things like, do we think this looks better? Do we think this looks better? We also have to be able to stack them. When you're going to make 1 million boxes of Kleenexes, you have to store them well, so your hexagons aren't going to be super great for that, you know?
Call me when they start making dodecahedral.
All right, I'll put it in my calendar to let you know when that happens. Okay, so I want you to talk with me for a moment about these things that are called discontinuities. So if you're going along with the graph and you get a hole, you've seen those before, right? And that's where that just doesn't exist. That means it's not continuous there. This is also a way to be not continuous. If it just stops cold with a dot, that means it stopped. That's not continuous anymore. Continuous means it just keeps going in both directions. That is continuous, and polynomials will be continuous. They won't have holes in them. If they have a hole in them, they're not a real polynomial. All right. So this is another really typical question, and we had it the other day, but I changed the numbers a little bit. Can you tell me the zeros, the multiplicity, and the behaviors? You don't even have to sketch it. Just try to answer what are the zeros. Hint, 3 is one of the zeros. See if you can fill out that little chart. I'm going to pause for a second while you do that. All right. Dice of destiny. Who should I call it on? It's row 4, person 3, Lillian Miller. What do you say? What are these 3 zeros, Lillian? 3 was one of them.
3, 6, and 9.
Perfect. All right. Next person. 6, 6. Ooh. It's only comes up once out of how many times? 6 choices. 6 choices. 36. 1 in 36 times, which is about how many kids we have, a little less. So that means go the 6th row and the last person. So good of you. What is the multiplicity of the 3?
3 is 5.
Yep.
These would be nice for me.
And 9 as well.
Good. And then the behaviors. Oh, and you're an expert on poor behavior. Just kidding. Thought you could handle it. So behavior at the 0 of 3. That first behavior, what would you call that? Is that well, hey, I'm going to give you a hint. Your answers, Owen, are either bounce or something that's not a bounce, which I hope you know the name of.
I think cut probably, but like the bounces happen when it's like an even. No, not when it's even.
So at the top one here, it's not a bounce. So what do you call it again?
Cut.
Cut through. Very good. I'd also accept pass through if it seems less violent to you.
Second one's a bounce. And
We called
the
those snakes
third one's
last
also a
year.
bounce.
Yes, but that's only if it was to the 3rd power. And I've talked to the calculus teachers, and they say there's really no difference to in calculus whether or not it's that special curvy one that's a snake versus just passing through. So we're just gonna not talk about that. Wait, let me finish this. Cut, bounce, and last one.
Cut.
All right,
How does one know if it's a cut or bounce?
good. How does one know if it's even? It's a bounce.
Okay, thank you. Appreciate it.
I'm tempted to just not tell you because I want to encourage you to watch the videos when you're gone. But-
I'm so confused right now.
All right. So then here's my 3. Here's my 3 zeros. 3, 6, and 9. Would you please sketch this? If that's 3, 6, and 9, what's it look like? You should know how it ends and how it begins. You should know where there's a bounce and where there's only passing through. It's row 4. Person 3. Lillian, it really likes you, but I'm going to take the pressure off of you and move back to Noah. Graph. You already graphed it, right? Apparently not. Okay, so I get to walk you through it. So on the left end or the right end, I always start on the right. Do you think it should be going up or down on the right, Noah? Hint, there's no negative here. Hint, hint.
It's going up.
Up on the right. Okay, now, Owen, behavior expert, which way is this going to go?
Oh, shoot. Well, it's gonna end.
Is it going to go right through the 9 or is it going to bounce
It's
up?
gonna end up going opposite ways. So
It's gonna do the.
It's going to do that.
it's gonna do that obviously because it cuts
And
it
then?
bounces on the 6.
Boing, and then
And then it goes.
Right, cuts through.
What?
just like that?
Well,
That's
no,
wrong.
no, this feels wrong.
Okay, so let's figure out, is it an even degreed function which should be going the same direction on each end, or is it an odd degreed function? Well, what you're really missing is the lead term. So I recommend this, and on the test, the kids who get these right usually have at the top that the lead term is x to the 5, 6, 7, 8th, dot, 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 don't care what's in the middle. And then they also have whether the answer to the y-intercept is really big or really small. Because see, both of those would help you. Would you agree right now to know the ending? If I knew that the y-intercept was really big, then I'd need to go up there, right? Okay. And if I knew that the y-intercept was really a big negative number, that would help too. So this one, it's negative, but it's to the 5th, so it's still negative. This one would be positive after I squared it. And this one would be negative. So I got 2 negatives and a positive, which means that it's going to come up to a large positive. Big pause.
Okay.
So it's a big positive. So I know it's headed up at the end. There, I'm done. That's the sketch. Okay, moving on. Let's get to this. Another one just like it, but let's not do it. If you should know how to do these though. Okay, moving on to actually the homework. I'm going to suggest you do the first one, not the middle one. And what are the zeros? I have this feeling we did something just like this the other day, but I think you could do this without too much effort at all. It does say check it with a graphing utility. You don't have to, but you could. But since you have a key, you might want to just check it against the key. All right. And on this page, strong recommend. Because my number one thing is if you can factor it, you should. What's my follow-up?
Clear the fractions.
Clear the fractions. And the other one is, after if you can factor it, you should, is if you can't factor, you could try the quadratic formula. All right, maybe I should write these down for you. If you can factor it, you should. Then if it doesn't factor, you should use the quadratic formula. That happened on your last test. And it was a lot of times where if the kid would have just stuck it in the quadratic formula, they'd have gone, oh, I guess I get a square root of a negative, so there's no solution. And then they could tell their answer that way. All right, so if you can factor it, you should. Can't factor it, you use the quadratic formula. But this thing's not a quadratic. You know why? Because I got to clear the fractions out. And to do that, what am I going to multiply everything by? X squared. And when I do that, do you get how that's going to turn into x to the 4th? So this is not a quadratic, but it's a polynomial. In the polynomials unit? Who would have thought? All right. Then I would do this one, number 9. I would not do the challenge. I would skip this one because it's just way too hard. But this one, strongly recommend. Remember me saying that yesterday, like, we really got to get to this problem. I'm sure you remember that from the video.
Oh, yeah.
And then I showed you how to do the box problem today. And then here's another box problem. All right. That's all I got for you for today.
Oh my gosh, I am so